Hello, I'm Nikunj Oza. I'm leader of the Data Sciences Group at NASA Ames Research Center in the San Francisco Bay Area. I'm very happy and thankful to be a keynote speaker here in the KDD 2020 Millets workshop and speaking about machine learning for aviation safety. Please accept my apologies for any funny sounds in this talk or anything funny that I say. In spite of all of these months of spending time working only at my computer and talking to it, I have not really gotten used to it, and certainly have not quite gotten used to giving talks at my computer here. So again, please forgive me. In any case, though, as I mentioned, I am leader of the Data Sciences Group, and in particular, we in the group do machine learning and data mining research and development for application to NASA problems. Now, NASA, of course, is most well known for human space exploration, but it also does significant work in aeronautics. In fact, it's the leading US government research entity in aeronautics, and also does significant work in earth science, not surprisingly focused mainly on remote sensing, so satellite-based measurements. And also we do significant work in space science, things like the Kepler and TESS mission to find Earth-like, possibly habitable planets. Now, our group currently has 13 members, and we always have students, certainly mostly in the summer, but oftentimes in the fall and the spring as well. And we're a mix of people like me who have a background in machine learning, and then we also have some who, say, got their degrees in engineering, but then they found machine learning to be useful in their work, got bitten by the machine learning bug, and decided to join us. Now, we get a variety of have a variety of projects within NASA. I will mostly be talking about our work in aeronautics, especially aimed towards commercial aviation. However, we do also have significant work in earth science and space science, where nearly all of the funds are awarded competitively. And then we have some also within human space exploration. And every now and then we do work funded by external entities that has a complementary nature to the work that we're doing at NASA. Now, as I mentioned, I'm going to be speaking here about our work oriented towards commercial aeronautics. Now, people may wonder why we would work on this problem, and these two graphs may lead you to wonder why. Now, as this shows, the number of flights run worldwide in millions here is what's shown, has been going up quite steadily. Now, as you might expect, the COVID-19 pandemic has led to a bit of a dip, but if the past is any indication, we actually will rebound and continue growing. Notice we've had dips such as, for example, the 2008 financial difficulties that happened. We had a little bit of a dip there, but then we recovered quite well. Now, as the number of flights has been steadily going up, the number of flight-related fatalities has been coming down reasonably steadily, all things considered. Now, and every sign is that it's going to continue decreasing. So you may wonder why we bother working on it. Well, the main reason is that the aviation system is not a fixed entity. It is constantly changing. We do expect continued increases in commercial air travel. So that are, of course, are obvious issues such as increased density of air traffic and therefore difficulties in coordinating them all. Then also with the increased demand for air travel, there's increased demand for aircraft, and we're seeing aircraft being maintained for longer and longer periods of time. So maintaining these aging aircraft has its share of difficulties. And then there's also the need to recruit pilots. There are countries where retired fighter pilots are being pressed into service to fly commercial aircraft, not necessarily with the best or ideal amount of training that should be done. So that has its share of problems. Now, there's also the desire to change standard operating procedures for aircraft when they take off and land because of, as I mentioned, the increased density, but also because of the desire for noise reduction and in fact also reduction in air pollution and improving fuel economy. Another problem is the increased heterogeneity in air traffic. We have an increasing number of unmanned aerial vehicles. You likely have heard many reports about UAVs interfering with commercial aircraft. Now, there are, of course, many benevolent uses of UAVs, but they do have to properly coexist with commercial air traffic, and that is already posing some problems, and the problems may increase further. Of course, I also brought up the COVID-19. COVID-19, the September 11th attacks, others have led to significant reductions or stoppages. And then that has its share of problems. Of course, operating in a degraded mode is difficult, but also as commercial carriers ramp up, you're restarting operations with aircraft that have been idled for a significant period of time, and in many cases, idled personnel who have maybe need to get their training up to date, have not had recent hours, and therefore are out of practice. Then there's also the problem of how to safely incorporate new technology and these various improvements, things like these changing procedures. There are going to naturally be teething troubles as procedures change, as improvements are introduced, so you have to expect some increase in difficulties there, but then there's a question of does the intended effect of these improvements actually take place? Are there any undesirable side effects that kick in as a result of these supposed improvements? These are all threats to aviation safety. Now, we of course have the desire to be proactive about all this, hence what is called NextGen. Now, today's system, it's relatively primitive. It has not changed very much over the last many years. We have navigation and surveillance that are ground-based. Air traffic communication is still done by voice. We have various information systems that have been introduced, so it's not like there have been no changes, but these systems are quite disconnected. Also, there's a notion of air traffic control. We have fragmented weather forecasting, and airport operations are still limited to a great extent by visibility conditions. And a key thing is that we are very forensic or backward-looking. Problems happen, we look back at what could have been done differently. There's the desire to change things. We certainly want to incorporate more and more new technology, sending information digitally, making use of satellites, air traffic management, where it's not just, say, what you call an air traffic control with people there managing everything. You'd like as much as possible the management to be distributed among aircraft, but where ground-based control is needed, one should be able to use that. We also want to have operations continue into lower visibility conditions. And then, of course, for UAVs, that's going to be important. We do not want to always have to be visualizing UAVs from the ground. It should not be like the traditional remote control planes where there's somebody on the ground and is always looking at the aircraft that he or she is controlling. That's not practical in the long term. But a big part also is that we want forecasts embedded into our decisions, and we want to be much more prognostic and predict. Now, NASA does have a role in this. As I mentioned, NASA is the main player in doing aeronautics research among federal agencies. Now, NASA has a project within its Aeronautics Research Mission Directorate called System-Wide Safety. And within that, there is a technical challenge for which I am the sub-project manager. This is called Integrated Risk Assessment for the Terminal Area. And the basic idea here is to collect or at least have access to these relevant data sources, use those independently and fuse them as needed to identify safety incidents and precursors to those incidents, with the idea of being able to predict, is something going to go wrong? Provide some kind of an alert, provide for decision support that will allow our key players to be able to mitigate those safety issues, ideally before they happen, but certainly before they degrade into something like an incident or an accident. Now, in order for our personnel to be able to implement these mitigations and have the benefit of this alerting, all of these tools and the data and visualizations, they need to be integrated into dashboards to allow for this risk assessment. And so that's also is a key component of this technical challenge that we're working on. Now, I mentioned the desire to identify incidents and accidents and predictors of these. Now, what are these incidents actually like? Now, the idea is the overwhelming majority of time, as we discussed, the aviation system is operating in a safe state. Now, every once in a while, there is a certain context which by itself is safe, but it has a higher than ideal probability of leading to what we are calling here a compromised state. Now, most likely, again, the system will recover. However, there is some chance that we may degrade even further into what I'm calling here an anomalous state. And again, most likely the system will recover, but there's again a small probability that we will degrade into, say, an accident where there may be the aircraft is lost, or even there could be like loss of life or injury, or there may be an incident where you have to stop operations, but maybe there was no damage that was done, but it's still something that would make the safety analyst's hair stand on end. Now, we want to be able to find incidents involving this entire chain going from context all the way through to compromised state, anomalous states, and these incidents. Now, in order to do that, we of course need access to data. Now, the kinds of data that we've mostly been working with include flight operations quality assurance. These are data that are collected on board the aircraft and then downloaded and are available for safety analysts. Another significant source of data we have been working with is trajectory or radar track data. These are data that are collected over an airport. You may have seen screens like this where every aircraft is represented by a dot, and air traffic controllers monitor these dots as they're moving around, and there's also information associated with them, like the altitude at which they're flying. And we want to make sure that the overall traffic around the airport is as you expect. There's proper separation, aircraft are maintaining proper altitude, are aiming towards the runway for which they are cleared to land if they're on landing, etc. Now, other data sources that we have worked with a little bit that I will not end up talking about here very much include aviation safety reports, as well as weather, and there are even other sources we've explored a little bit, such as pilot blogs. Now, I've mentioned the types of data. Now, the types of problems that I'll be talking about here are anomaly detection, which is, as you might, all of you probably know, is just identifying individual anomalies within the flights and any kind of safety issue. But another key problem that we have been working on is precursor identification. So this is identifying what I called the context in an earlier slide, where by itself it may not be a safety issue, but there is a higher than normal probability of ending up in an anomalous state. Now, what I will not be talking about here is some of what we have done with aviation safety reports, which are in the form of text, which includes classifying the reports into different anomaly categories, and then also topic identification. So this is using things like latent Dirichlet allocation or non-negative matrix factorization to take a set of safety reports and identify what seem to be the key topics represented there. Now, there is increased use of machine learning these days within the aviation system, but overall still the dominant method of finding issues is what are called exceedance-based methods. Here in this audience, if I talk about rule-based methods, you'll right away know what I'm talking about. So the idea here is that we are looking for known anomalies or safety issues that are typically conditions over 2 to 3 variables. So here is an example actually of a high-speed exceedance. So during landing, when the altitude is 1,000 feet, if the aircraft's speed is greater than 250 nautical miles per hour, then that is a high-speed exceedance. Now, pretty much by definition, these exceedance-based methods are good at identifying known anomalies, but pretty much cannot identify unknown anomalies. So that's where about, 13 years ago at this point, we decided, as NASA decided, to go into looking at data-driven methods. So this is machine learning and data-driven methods to discover anomalies, essentially by doing what we all know as anomaly detection, essentially learning the statistical properties of the data and find which data points seem to not fit with the rest, in the sense that they are somehow far away from or of low probability. One interesting thing, the reason why I have capitalized the word discover here is because the first time I gave this presentation, it was to an air carrier, to some of their safety personnel, and after seeing this slide where I talk about anomaly detection and letting the data speak for themselves, someone asked me how we actually tell the system what kind of problems to look for, when in fact I just got through saying that we are just letting the data speak for themselves, not giving the algorithms any kind of preconceived notion of what to look for. I'm not saying that aviation safety analyst is dumb in any way. I'm just pointing out that this was such a paradigm shift when we were first getting into this industry. Now, these methods, data-driven methods, are of course complementary to existing methods. Now, these methods do have a lower false negative or misdetection rate because we can assume, given what I described about how safe the aviation system is, that all data points that are statistically normal, that happen relatively frequently, represent operationally normal behavior. I think that's probably a pretty safe assumption. So you can say that you're not going to probably miss safety issues within this statistically normal set. Unfortunately, you do have a higher false positive rate with anomaly detection. We all know about this, that within the set of statistically anomalous methods, there are going to be a fair number of false alarms. And then we know there are going to be some known problems, but the key thing that we're interested in finding are these unknown problems. Now, the overall methodology that we have been working with that actually has been successful is that we have used these data-driven methods, and yes, we've had to filter through some false alarms, but we have identified some previously unknown safety issues, and that has actually led to a modification of the exceedance-based methods at least one air carrier that we have worked with. Now, this is an example of the kind of problem that we found. Now, this is a case where the aircraft is taking off. As you can see, it's going from ground level, going up steadily as you would expect for a takeoff. But this particular flight, while taking off, had a significant drop in its airspeed. Now, this drop in airspeed continued for about 30 seconds before finally the aircraft climbed. Now, this particular flight showed up as particularly anomalous because the drop in airspeed came to within only 12 knots above the estimated stall speed. Now, we did not give the algorithm any kind of sense of what stall speed is. It just looked at this combination of variables and just said, okay, this is weird. Now, another anomaly of the kind that we'd like to find is with the discrete variables. What I showed before dealt with continuous variables, altitude and airspeed, and now this is dealing with discrete variables, in this case autopilot modes. So in this case, it turned out the human pilots and the autopilot were actually fighting over which mode the autopilot should be in, whether it should be the vertical speed or altitude hold mode, and eventually the pilot just got frustrated and decided to actually recycle the flight director. So this particular flight showed up as anomalous because of this unusual switching sequence. You don't see that many changes typically. Now, these two anomalies that I have described so far are with data that are collected on board. This is an example of an anomaly found with radar track data. So what you see in gray are lines that represent trajectories, landing trajectories on this particular runway here at New York's JFK Airport. What's shown in orange is a flight that was found to be anomalous. Now the reason for that was that this aircraft overshot the runway when it was trying to land. It was not able to line up in time to be able to land properly, and therefore it was likely directed, or it may have chosen to go around and try landing again. Now, you may just barely be able to see that the aircraft actually managed to overshoot the runway again, but this time was able to line up before the hour marker and therefore was able to land properly. Now, this is a little animation, just this may perhaps wake up those who decided to sleep here. And now what's shown in red here, this is the target aircraft, the one that was found to be anomalous. Now, you can see here that this particular aircraft is going to land at LAX, but it does not go far out enough to be able to make its turn. So as you can see by this dotted line, it's actually going to overshoot the runway that it was supposed to land on and get instead as if it's lining up to land on the other runway. Now, please don't be afraid here. These aircraft actually didn't get that close. There was pretty good vertical separation there. But you can see it's still not good to be over the parallel runway. And he tried desperately to get over, but then ended up again, overshooting the runway on which it was supposed to land, but then finally was able to line up and land properly. And this one, yeah, as you can see, it's a 747, so it needed a little bit more space. He should have probably taken, a greater amount of space in order to make its turn. Now, all of these anomalies that I described, whether on the onboard data or on the radar track data, were found by this algorithm we developed called the multiple kernel anomaly detection algorithm. This is it's a one-class SVM that of course had been developed before, but we developed a multiple kernel version of this. And so in particular, we were able to use we used a discrete kernel for the discretes, for example, the autopilot modes, the anomaly that I showed earlier there. And then we had a continuous kernel to use over the continuous variables. And we've done very little experimentation so far with the text kernel, but at least in principle, you can use it with text and other variables. And of course, the fundamental idea, most of you probably know, is to take these heterogeneous data types and use kernels to map them all into essentially the space of 0 to 1, where 1 is maximum similarity, 0 is maximum dissimilarity. Now, the discrete kernels that we used were the normalized longest common subsequence. So in this, through the discretes, essentially, if two flights have exactly the same sequence of switches, then the longest common subsequence would be the entire sequence, and therefore that would map to a similarity of 1. Whereas if two sequences were very different, its longest common subsequence would be pretty small, and that would translate to a similarity that's much lower. Now, for the continuous, we also did use a normalized longest common subsequence, but we used the symbolic aggregate approximation representation that Eamon Kjog and his folks pioneered. Now, for the text kernel, when we did our work with it, we actually projected safety reports that were received onto the topic vectors that were identified using latent Dirichlet allocation that was run offline on some very large corpus. And using the Euclidean distance between those projections allowed us to see how similar two safety reports were. And now for the case where we had normal flights, which was of course the vast majority of them, we still had to have a safety report because we could not have, with the multiple kernel learning method, any missing data. So we actually just generated random reports using the various words in that corpus. So of course, those reports would not really line up with any particular LDA topic, and therefore would be evenly distributed over the different LDA topic vectors. And so in that way, they would be very different from actual safety reports, but they would be quite similar to other normal flights that were also randomly drawn and therefore do not project strongly on any LDA topic vector. Now, I mentioned the problem of a high false positive rate. So I'm going to show what we did about that, and then I'll show you some results that we got with both the MKAD, the one class SVM, as well as the method that we used to try and reduce the false positive rate. Now, what we used for this is essentially a classifier. So when the anomaly detection method says that data are statistically normal, we just assume that they are operationally normal. But when our anomaly detection method says that a data point is statistically anomalous, we pass that to a classifier and we ask it, is that example actually operationally anomalous? So falling within this set of two here, either a known or an unknown problem, or is it basically a false alarm, just something like a data glitch? Now, since our domain experts don't have a lot of time, we used active learning. And now the way we did it is by first taking a bootstrap sample among the set of data points or flights identified as anomalous by something like MKAD. We would draw a bootstrap sample, review the flights, learn a classifier, come up with something, but then now we identify which is that one example that we want the domain expert to classify that's going to give the biggest bang for the buck. Let the domain expert review it, update the classifier, do a re-ranking. Hopefully it's not just one example being re-ranked, but maybe several others that are similar also being pooled up to be ranked as more anomalous, while some of the false alarms maybe get further suppressed. But here in this illustration, I'm being a little bit pessimistic. So now, of course, we do what you would expect, which is now find the next flight that would give us the biggest bang for the buck. And we do this again for as long as the domain expert has patience to actually do this. Now, this is a screenshot of an annotator that we developed. So the idea is that when we pick an example for the domain expert to label, he or she will get a window that looks like this. The domain expert can see these various variables, and then we actually do illustrate. Our algorithm actually gives this red line essentially showing which are the data points that are outside, in this case, the 10th through the 90th percentile. And then we allow the domain expert to actually make these boxes. So essentially say, okay, which is a range of values for these different variables that actually is funny. And then we also allow the domain expert to enter a rationale in the form of text here. And we use that to actually extract features that are then used by the classifier to determine whether a statistically anomalous flight actually is operationally significant or just a false alarm. This is used to essentially update that classifier. Now, this is an example run that we did in our work here. So we identified a set of landings at the Minneapolis-St. Paul Airport, and there were overall 78 non-operationally significant anomalies and 20 operationally significant anomalies. This was determined offline. And then we looked at the characteristics of the flights that were ranked in the top 46 among MKAD and after doing active learning. And in this case, the active learning came after looking at about 20 or so flights. We said, okay, at this point, what actually are the true positives and the false alarms? And the key thing here is that active learning ended up detecting or having 4 more operationally significant flights in its top 46 ranking compared to what MKAD had, and then also 4 fewer false positives. Now that may not seem like such a large number, but remember that these, what we're talking about, are safety issues, so there typically are very few in any case, so detecting any one is actually quite notable. Now what I described here is really identifying individual anomalies at a given point in time, right? Like I showed, okay, for a given landing, maybe its trajectory looks a little funny, or for a given takeoff, we also have a drop in airspeed, but it's a contiguous period during which an anomaly is taking place. Now, I mentioned here that we're really interested in identifying this chain of events, and in fact, you don't necessarily even have a steady degradation. You may have some kind of a context under which maybe things look perfectly normal most of the way, but then a problem pops up much later. So we also want to identify these precursors, these contexts. And so that's where precursor identification comes in. So this is kind of a cartoon description of what we're trying to do. So there's the notion of a safe state and a hazard state, but we want to find what is that earliest point at which we can say, something happened where most of the time it would go on a track towards being in a safe state, but for some reason instead it went off track, and there's a higher than ideal probability at this point that you're going to end up in this hazard state. Now, it is possible that once you end up on track towards the hazard state that you could actually correct yourself. So we certainly do want to look for that, but we sometimes find that there are corrective actions taken, and then sometimes things degrade again. So we want to find this entire sequence, whatever shows up in the data. Now, this is an example of the kind of anomaly that we want to find. So in this case, we are looking for precursors to go-arounds. So you saw that go-around that I presented earlier. We'd like to find what is a precursor to that. Now, an obvious one is one that you saw earlier, where the aircraft was not lined up for not lined up for landing before the outer marker. But this is another example. This is a case where the aircraft was going too fast. So in this case, the algorithm said that the ground speed is higher than the normal range. And then it turned out also this particular aircraft had a vertical closing speed to the nearest aircraft that is more than ideal. Probably was getting too close to an aircraft that was in front. And so then in that case, chances are the aircraft was directed to go around, or maybe on board they realized that they probably would need to go around. Now, we so far have developed two algorithms for this. One is this algorithm called adopt, where the idea is that you give it, of course, a large number, or however many you have, of nominal time series, and you give it some adverse time series. So these would be time series that have, for example, go-arounds in them. Now, we use inverse reinforcement learning to essentially assume that the majority of these flights are nominal, and so chances are it's maximizing the reward, and therefore that inverse reinforcement is yielding what we call the expert's reward model. And then we use reinforcement learning from that to generate what is the expert's value model. Now, in this case, what we're assuming is that a low reward state corresponds to an undesirable effect, such as go around. A low value state corresponds to the precursor. So, for example, getting too close to the aircraft in front or going too fast, that has a higher than ideal probability of leading to a low reward state, and therefore that precursor itself is going to have lower value. And that's what we were able to use here in order to identify precursors such as the one that I showed on the previous screen. And it turned out we have been able to use this algorithm to find several precursors in both the FOQA data recorded on board and also the trajectory data. And we have also been able to use it to find some corrective actions. We've done some preliminary work where we have been able to see this ability to identify corrective actions. Now, we also, though, developed a new algorithm following that respects the notion of safety within an entire flight and safety within portions of a flight a little bit more. So this is using the framework of multiple instance learning. So we're assuming here that that a flight is safe if every time period within that flight is safe. However, a flight is unsafe if any data points within that flight represent unsafe operation. Now, There's a problem here, as depicted here, as is typical in multiple instance learning, there is no temporal component. And therefore, that's where we came in. We developed deep temporal multiple instance learning, where up here at the top, this depicts the notion of multiple instance learning where, as I mentioned, if any of these time points within the flight are unsafe, we say that overall the flight is unsafe. But below that, we're using the gated recurrent units to take the temporal nature into account, and then using the fully connected layers to then go into then determining for each time point, is the flight actually safe. Now, this is that's a set of results specifically for the case of the high-speed exceedance, which I described earlier. This was the case where during landing at 1,000 feet, the aircraft is going too fast, at say more than 250 knots. And so this is just showing that our deep temporal multiple instance learning, or DTML, ended up performing the best. You can see from here that there is a value to having the temporal component. There's also a little bit of value to having something deep rather than a shallow network. So there is actually at least a little bit here to learn. And then this is just showing using a multiple instance SVM formulation, whether you have a temporal component or not. That does not do quite as well as the DTML with the gated recurrent units. And this is showing the result here of using adopt, and notice that we do get a pretty good improvement on that, especially in terms of the generalization. There, of course, are many more tests to be run, but we always have the problem of there not being that many anomalies on which we can test. We're fortunate to be in a world of a rather safe aviation system. Now, overall, I've described these two different approaches. Now, the key differences between these two approaches, the adopt, which is a kind of a reinforcement learning and inverse reinforcement learning based approach, versus the DTML that we have seen, the differences we've seen are that with the adopt, we're able to deal with the simple cases more easily, and also reinforcement learning inherently has a notion of actions. So that makes explaining the decision making much easier. It's much easier to lay out to a domain expert what were the actions that maybe led to that adverse event happening, as opposed to not. However, there is drawback. With adopt, dealing with complex data overall has been difficult. There is fundamentally that state space explosion that does take place when in reinforcement learning, and that is difficult to deal with. And overall, the algorithm we found pretty slow to determine the optimal actions. Now, with multiple instance learning, the DTML, we were able to capture some more complex interactions overall. The algorithm is more scalable, and then you saw we, at least so far, have gotten better predictions performance. However, that notion of actions is now not there. We're losing that interpretability. And so currently we are working on trying to kind of merge the best of these two. Now, that's the work that we've done so far. There, of course, is much to be done. Within the anomaly detection and the active learning, I described the results that we've obtained so far, but certainly further testing of the algorithm needs to be done for a greater variety of flights and airports, and we need to further develop that user interface. We are working with MITRE on doing this right now, getting their feedback with the idea of ultimately deploying our algorithms for their use. MITRE is the main analytics entity or for the FAA. We also want to allow for the incorporation of multiple anomaly detection algorithms into the system, multiple active learning strategies, and also multiple users. We may have multiple domain experts providing their labelings. They're going to be colored by their experiences, so we want to be able to account for the user's characteristics. Now, within precursor identification, we have what I described earlier, the ongoing work to try and incorporate a notion of actions within the algorithm to make it easier to interpret the results. We have not done much work so far with text, with aviation safety reports. We would certainly like to do so. The redacted versions of the Aviation Safety Reporting System reports are available. They are publicly available, but within the company that runs this system, they do keep unredacted reports for the last 6 months. We would like to find a way to maybe use those unredacted reports, capture more of the essence of what's represented in those reports, to be able to do better analysis over time of what kind of reports are actually coming in. But of course, we want to make sure we don't reveal any confidential information in the process of coming up with our summaries. And then I mentioned a little bit about the desire to use non-traditional data sources. We have done a little bit of work looking at pilot blogs. So the thought there is that, say, an airport or a carrier changes procedures, maybe pilots may complain about these on pilot blogs. So in that way, the blogs may serve as precursors to actual incidents that may take place. Now, one work that I did not describe is work that we did on a multivariate time series search algorithm, where we can take a motif such as what I showed earlier with the altitude increasing but the airspeed first going up and then going down, and our algorithm, the MTS search, is able to quickly look through a large repository of flights for a waveform of that sort. However, for practical use, we do need a more space-efficient index on which to be able to do the search. So we do need to work on that, and then of course incorporating those into software that we might deploy. Then I've described also the need to incorporate other data sources such as weather data, maintenance, and then there's also needing to work on the user interface and also maybe different ways of visualizing data and the anomalies and the precursors. So please feel free to contact me, and we have this selected set and plenty more of bedtime reading if you'd like. Thank you so much.